Get serious. I'm glad to be here, and it's a pleasure to introduce Professor Marcio Carvalho, who is going to talk about microfluidics as a tool to study complex two-phase flows in porous media. Okay, welcome, Marcio.
So thank you, Claudio. And so good morning, everyone. Thank you all for being here after the great dinner of yesterday. So I know it was probably not easy to wake up and be here early in the morning. I want to thank the organizing committee for inviting me to give this talk, and especially Lais for all her work of organizing this event. So what I'm going to discuss here today is the use of microfluidics in a different application than what we saw up to now in this meeting. So I think that shows the multidisciplinarity of microfluidics and how broad this area is. To put this in context, I'm going to describe the research that we do in our lab. So we are fluid mechanics lab, and we focus on studying applied capillary hydrodynamics. So the common denominator of everything we do is flow of immiscible liquids in small scales, where capillarity is very important. So capillarity dominates most of the physics associated with the different phenomena. So we developed and used numerical methods and flow visualization and measurements on different applications. Here's the main 4 areas that we work on the lab. The first one is coating process and the deposition of thin film. This is my original area of research where I did my PhD. Then I worked at the 3M Research Center in Minnesota for a while. And then when I came back to Brazil, I wanted to broaden the areas of research, looking for application where capillarity hydrodynamics was important. And then flow in porous media was a natural choice. Then I got involved in porous media flow. Most of the work that we do is focused in enhanced oil recovery and now CO2 underground storage. Then we got into emulsion formation and stability, and most recently in microencapsulation. So we use microfluidics as a tool to study these 2 main applications. So complex flow in porous media and microencapsulation. So here's what we use microfluidics for in the lab, as I mentioned. So the first area that I'm not going to talk today is microencapsulation. So we developed different types of microcapsules for different applications, creating the capsule from a double emulsion template where the middle phase will reticulate and form a solid shell. And then we developed these for different applications in order to target or control the release of different chemicals. We won the ANP Technology Innovation Award some years ago for some of the work that we were doing in this area. So here's 3 applications that we have worked on. I hope you had a chance to see. Going back 1 slide. Okay. So hopefully in the poster session you got a chance to talk with Mateus and Ademir. They talked some of these applications. One, we encapsulated hydrochloric acid to control the dynamics of the gelation process. And also we encapsulated drag reduction agent to enable use drag reduction in undersea applications. And so there are different applications that we develop these microcapsules. The other area that we use microfluidics for is to study complex flow in porous media. So we have worked on studying the effect of viscoelasticity of polymer solutions in porous media flow, the effect of the wettability of the walls when water is displacing oil in a porous media, and also foam formation in porous media, getting the dynamics of foam formation, try to correlate pressure gradient with lamella and bubbles formation. And today we are going to discuss here 2 work that we are currently finishing up doing. The work in fracture and valvular porous media, and work of emulsion flow in porous media. So this is what I'm going to be discussing in this lecture here. So as a general introduction of porous media flow, for those who are not familiar, complex flow of porous media occurs in many different applications. 2 of them I already mentioned that we are mostly focused in our lab, which is the oil production. So typically you inject an aqueous phase to displace the oil phase towards the producing wells. So there's a complex 2-phase flow occurring in the porous media. And the same physics apply when you're trying to store CO2 in saline aquifer or depleted gas reservoir. So the goal is different. Now instead of displacing or maximizing the displacement phase, you wanted to trap the phase that you're injecting, the CO2. But it's also common application is the flow of blood through tissues, where it's a porous media where the blood is flowing through. The big challenge in studying porous media is that typically you're interested in a macroscopic behavior. Think about an oil reservoir. It's kilometers, its size ranges from kilometers. But all the physics occur in a microscale. So in order to try to develop or to understand this macroscopic behavior that you're interested in, you need really to understand the physics in the pore scale and do this upscaling of the physics from the pore scale to a macroscopic scale. So that's where we focus in our lab, try to understand this microscopic flow, to try to develop accurate models and optimize this process, but are macroscopic processes. And microfluidics became a very important tool in the understanding of these pore scale flows, because of the development of microfabrication methods allowed to construct models that are more closely related to the geometry of porous media. So there's this now almost old paper where they brought this concept going from a lab on a chip to a reservoir on a chip. Try to create a microfluidic model that resembles some of the characteristics of a reservoir, such that you could do experiments on this microfluidic model, not in a rock or running experiments that are very time-consuming, very expensive, and so on. So microfluidics more and more is being used by the oil and energy for different applications. One is to understand this pore scale physics, and the goal here is to try to develop more accurate models that you put in your reservoir simulator or in your optimization softwares. It's ideal to study the effect of pore space, because since you're constructing your model, you can control whatever geometry you're putting there. That's not true when you're getting a piece of rock and you cannot see all the details in terms of the pore space of that rock, because there's a limitation of resolution, how small a pore can you see, and so on. When you run experiments to screen different fluids, is this polymer going to work better than that, or is this surfactant going to work better than the other surfactant? Instead of running experiments that sometimes takes weeks to run in a core flooding experiment, you can do that in a microfluidics. It will take a few hours, so you can run through very different, large space parameters. So it's much faster and lower cost, and you can use small volumes of fluids. And so we are going to discuss, and I'll present two stories here. The first is the work of two-phase flow through vulgular and fractured porous media. This work came from a master's thesis of Jesus Daniel, who was co-advised by Jorge Avendano, who is a researcher in our lab. And now Vivian Mendes is finishing up her master's thesis, which is co-advised by Brenda. So if you have a very tough question, Brenda is here to try to answer for you. So what's the idea of vulgular or fractured porous media? Is this image tells you everything. So you have a rock. So there's like small pores that you cannot see in this scale. But also you have like these huge pores and fractures through the rock. Okay, so now the presence of these vugs, which are basically these macropores, and the fracture completely changes the dynamics of the two-phase flow, because you create areas where the liquid is very easy to flow, so that's going to completely change the dynamics. So what we are trying is to understand what's the effect of these vugs and these fractures on the dynamics of the flow. So here's basically what we want to see is both in a single phase and a two-phase flow. If I have a porous matrix that I understand well the dynamics of the flow through that porous matrix in terms of characterizing the permeability and the relative permeability curves that describes the dynamics of this flow, what happens now if I have vugs or if I have fracture, how that changes how water displaces oil, how CO2 displaces brine, and so on. So that's what we are going to be focusing on this research. So again, for this, we use microfluidics to try to understand some of that physics. I'll start with the vulgular system. So we created different porous media micromodel. One only contained a porous matrix, and the porous matrix was a regular network of capillaries, and we had 3 sizes of capillary throats, which were randomly distributed through the model. So there's some heterogeneity on the resistance of the flow through each of these pore throats. So we have pore throats ranging from 45 micrometers to 100 micrometers. We build these by using soft lithography with PDMS chips. And then using the same porous matrix, we create vugs of different sizes and different aspect ratio and different concentrations of vugs. So what I'm calling here this T1 design, I have vugs that have an aspect ratio of 1.7, and then we have like these elongated vugs which are aligned in the flow direction. And then we have basically a smaller concentration of vugs in another design. So we use, the fluids are here. We use a mineral oil phase and an aqueous phase. They are dyed with fluorescent dye, so everything you see in yellow in the videos that I'm going to show is oil. Everything you see in blue is water. So we run an experiment. We put the porous media micromodel there. We inject the fluids. We can measure the pressure difference of this flow. So that is the macroscopic flow behavior. It's the relationship between flow rate and pressure difference. But then we can see the physics in the pore scale, so we can relate what's happening in the pore scale, what's happening in the macro scale, trying to get these types of relationship. In order to construct the relative permeability curve of these flows, we follow the following experimental procedure. We start with the micromodel saturated with oil, which is here. So we inject with a syringe pump with a given flow rate. We measure the pressure difference so we can get what's the permeability of this porous media. And then we start having the two-phase flow. So we inject the two-phase water and oil at a constant total flow rate, and we change the ratio of the water flow rate to the total flow rate. Okay, so this is what we call a fractional flow of water. And we start from no water with F equals 0, and we slowly increase the amount of water that I'm injecting in the system. We wait for steady state, and steady state here is characterized by a pressure drop that doesn't change on average. So it's an oscillatory signal, but on average the pressure drop is constant. And then we measure this pressure drop, and then we take an image of the whole porous media. So for example, here's an image at the end of a process. You see that you have yellow and blue scattered throughout of the porous media. So part of the pore space is occupied by water, part is occupied by oil. So we can construct the relative permeability based on these pressure drop measurements. So let's start here. So F is how much water you're flowing with respect to the total flow rate. So when F is equals 0, you only have oil flowing. So as expected, if I have a porous media without VUGs, I need a higher pressure difference to pump that flow rate. If I have VUGs, I'm creating regions of easy flow, so the pressure drop is going to decrease. So this makes sense. As we increase the fractional flow rate, the pressure increases, and this is associated because although I'm substituting the oil by a less viscous liquid water, they are competing for space to flow inside the porous media. So I need a higher pressure difference to drive this two-phase flow. And there's capillary pressure between these two phases that I need to overcome to have this thing flowing. Okay, so the pressure drop increases. And then it comes to a point that I'm putting so much water in the porous media, and water is less viscous than oil, and the pressure drop starts to drop. Until here at the end, I have a pressure drop associated with water flow only. So there's some oil that's trapped in the porous media, but only water is flowing, oil is not flowing in this case. So if we look at the data for the same experiment, but now with the vulgular porous media, as expected, the pressure drop in the vulgular porous media is always smaller, but you can see that there's a range where the pressure drop doesn't change, and the difference of pressure drop with the media without VUGs and with VUGs is much higher than what you get with the single-phase flow. So that's showing that the two-phase flow is really becoming strongly affected by the presence of these VUGs. So here's just an example of the state of the porous media at this condition here at steady state. So another thing important for oil recovery is that you want to know how much oil you're able to displace from your pore space. Okay? So we want to achieve at the end the smallest residual oil. Oops, sorry about that. So you want to reduce the, I'm sorry, these videos make this presentation very heavy. So you have the amount of oil that's left in the porous media is very important, and ideally you don't want to see a lot of yellow, because if you see a lot of yellow, it's basically oil that's in the porous media, and you don't want that. You want to get that oil out, okay? And so we map what's the oil saturation as a function of the fractional flow rate for the system with VUGs and without VUGs. Okay? And again, a bad news here for oil recovery is that if you have a vulgular porous media, the oil saturation that you get is higher. So it's harder to take oil out if you have a vulgular porous media. Okay? And you can see this, we get the saturation by image processing these images, and you can see that there's more yellow in the porous, the matrix here, than what we had in this top plot here. So at the end, we can use the saturation data and the pressure drop data to construct the relative permeability curves. So the curves in black are the curves without VUGs. So this is the water permeability. So as the water saturation increases, the water permeability increases. Makes sense. There's more space for the water to flow. And as the water saturation increases, the oil permeability decreases, and again, makes sense because you have less space for the oil to flow. If we put VUGs, important point here is that the oil relative permeability is very little affected by the presence of VUGs, and it's important, I didn't mention, I ran by this. This porous media is oil wet, okay? So, which is most of the carbonate are oil wet. So the important conclusion here is that the wet phase is not affected by the presence of the VUGs in this case. But now the water permeability changes quite a lot. So the water becomes, when I have VUGs, the permeability of the water increases. It means that it's easier for the water to flow, okay? And the reason is that the water tends to go to the VUGs, and then it flows easily through these VUGs. So that's why you get this higher permeability on the VUGs, and the oil, you don't see a strong difference on that. So this is bad news for oil recovery. We also looked at the different geometries. What's the effect of the aspect ratio of the VUGs? And I will just focus on this plot on the right here. So T2 is the design with the elongated VUGs, and T3 is the design with the more squared VUGs. And again, you see if you elongate the VUGs along the flow direction, you get an even higher water permeability. And if you have a high water permeability, again, this goes against displacing oil, because the fluid is going to flow the easy way out. So if it's easy for the water to flow, it means that the oil won't flow. And you want the oil to flow because you want to displace the oil. So the whole idea of this research is trying, okay, how can I go and put in a macroscopic model the effect of a VUG inside a reservoir scale model? Because in a reservoir scale model, you won't have enough resolution to describe the presence of VUGs there. You're going to have a single cell on your model that has a lot of VUGs in there. And then you want to describe that behavior in a single function. So that's what we are trying to get here. So we extended this work with Vivian's master thesis, trying to look not on VUGular system, but now system that has a fracture going through it, okay? And so again, it's the same porous matrix with the fracture. We are looking at different geometries of fracture, and again, we use PDMS to make these devices. The experimental setup is very similar. So we have syringe pumps where we pump the two phases. We measure pressure drop. And here is showing, so water is dyed in blue here. Oil is transparent. So you can see the water and oil flowing through the VUGs and also flowing through the porous matrix. And the experimental procedure is exactly the same. We vary the fractional water flow, keeping the total flow constant. And then we go from a fractional water flow from 0 to 1. When we reach steady state, we get the images and we get the relative permeability curves of these fractured media. And an important question is that we know the relative permeability of the porous matrix. So the question is that how can we put the effect of the fracture on the relative permeability of the coupled system, where I have the porous matrix and the fracture? So in a sense, we would have to make an average of these two systems, of the porous matrix and the fracture. So the first thing Vivian did was try to measure a relative permeability of a fracture alone. So this is flow through a pipe or through a channel, okay? So she isolated the fraction, so there's no communication between the fracture and the porous matrix. So this is, again, a flow through a pipe. And we inject both fluids, and then, again, we measure pressure difference and get the saturation. And then here, reveal a very important phenomena that reveals the importance of the visualization of the microfluidics used to understand porous scale flow. In the literature, what 99.9% of the research that's done in this area assumes is that the flow resistance or the relative permeability curve of the water and the oil phase is like a linear function of the saturation. Because if you have a pipe and if you have liquids flowing in slug, that's what you're going to get if you work the Poiseuille equation on that, okay? But you can see that clearly there's a transition from a slug flow through a core annular flow. So if the water saturation is high enough, remember this is oil wet, the oil is going to flow attached to the wall and the water is going to flow through the middle. This completely changes the pressure difference that you get in the flow, okay? So you can see that the relative permeability of the oil and the water has a huge jump here when you get this transition from a slug to a stratified flow. Okay, so that can explain a lot of phenomena that's seen macroscopically when you do a core flooding experiment, but you don't really see what's going on inside that rock. So we can measure now the coupled system. So now again, we are injecting water and oil. Water in this case is blue, oil is transparent. And then, but now the system is coupled. So there is mass transfer between the porous matrix and the fracture. And again, you can see again the transition from a slug flow regime to a continuous flow regime, to a stratified flow regime. And then with the pressure drop, we can measure the relative permeability curve. So the pale curve is the relative permeability curve that we get from the porous matrix alone. So if there's no fracture, that's the relative permeability curve. There are two important variables in this curve, which are the saturation, the minimum saturation of water where water starts to flow. So it's the point where the water relative permeability goes away from zero. So this is called the irreducible water saturation. And another important one is the residual oil saturation. It's the point where the oil relative permeability reaches zero. So at this point, with the water saturation of around 55%, so the oil saturation is around 45%, oil doesn't flow. So that means that 45% of the pore space has oil that does not flow. So this is bad news if you're trying to displace oil. If you put a fracture, it gets even worse, because now like the residual oil saturation went from 45% to 55%. You get more oil trapped inside that porous medium, okay? And you get an increase in the water relative permeability curve, and you get a decrease in the oil relative permeability curve. More bad news. Again, it's easy for water to flow, it's hard for oil to flow. This is not good news, it's hard to displace that oil. So that shows the challenge of displacing oil if you have a fractured porous medium, okay? Again, these results can be, what we are moving now is what Vivian is working on, is try different geometries of fracture and then come up with a correlation. How can we associate the geometry of the fracture to these changes on the relative permeability curve that we get with respect to the porous matrix? So as final remarks, I think I already mentioned all of them here. But I think the important point here is that the fundamental understanding of the single and multi-phase flow through the vuggy and fracture porous media will enable more accurate reservoir scale models. So this physical pore scale understanding is critical to develop accurate model that can be used in optimizing reservoir production and so on. Okay, the second story is flow of emotion. There is supposed to be a picture here, probably massive. This was part of the PhD thesis of Clarice de Amorim. She just defended her thesis last month. And what we were looking here is injecting oil in water emulsion as a way to displace more oil. So again, just getting an idea of what was the goal of the project. If we are injecting water, water will force the oil towards producing wells. But even in the area where the water swept the reservoir, there's going to be a certain amount of oil that's trapped and it doesn't move. Is that residual oil saturation that I mentioned a few minutes ago. So if I want to mobilize this oil, if I want to produce this oil, I need to win this battle between the pressure drop in the aqueous phase and the capillary pressure that's keeping this oil trapped, okay? So I can do this by two ways, reducing the capillary pressure, for example, by injecting surfactant, or I can increase the pressure drop of the water phase. I don't want to increase the pressure drop of the water phase in the whole flow since I'm pumping the liquid from the reservoir, from the platform, because I would waste a lot of energy just to pump that water. So I want to locally increase this pressure difference instead of increasing the pressure difference in the entire flow, okay? So that's where the idea of emulsion comes into play. So and this idea is not new. There is a pilot trial in a field in the US in the 60s. So this is oil production, the continuous line. It came, so as time was going, the oil production was going down. It came to a point that inject water with tiny oil drops dispersed, very dilute. So if I get this emulsion and put in a viscometer, it's going to be the same viscosity of water. It's around 2% of oil, same viscosity of water. And then what they saw is that after a while, the production of oil went up, okay? So they were able to produce way more oil than if they didn't do anything. After this work, oil became cheap. Nobody cared about enhanced oil recovery. But then in the 90s, again, this became important. There were trials of using emulsion. In some cases, it worked. In some cases, it didn't work. So the problem is that you need to understand what was going on, and more importantly, how to design the emulsion that would work in your reservoir. Okay, so that's the big point that we are trying to address. So we got on this area in the the first thesis came out in 2012, so more than 10 years ago. And here's a core flooding experiment that we did. So we got a plug saturated with oil, inject water. We display, this is volume of oil produced. After a while, we are injecting water and getting water out. There's no oil coming out. We were able to recover only 33% of the oil. So 70-something% or 60-something% of the oil was trapped in that plug. We inject a slug of water with small oil drop. The injection pressure goes up because now I'm forcing these drops to go inside the porous media. I stopped injecting emulsion, go back injecting water, the pressure goes down, and then the recovery goes from 33% to 40% and then to 55%. So there was a huge increase in the production of oil if I do the things right. So the question is that how can I design an emulsion to work in a certain reservoir that I want to work with, okay? So that's what we got in working on. So the basic concept is that if you have an oil drop flowing through a pore throat, if the drop is smaller than the pore throat, there's no problem. The drop will just flow without any effect, okay? If the oil drop on the right side, it will get trapped by capillarity. And in order for this drop to go through the pore, I need to have a pressure drop that's higher than the capillary pressure associated with the change in curvature of the tip of the drop, okay? So I change the resistance of the water to flow through that pore throat. So it's as if the water became more viscous in that pore throat because I'm partially blocking that pore throat. And the basic idea then is that if I inject water, water creates an easy way out, so there's oil that's trapped. If I want to displace this oil, what I want to do is that if I inject now emulsion drops, if the drops block the path that the water had already created, the pressure is going to go up because I need to force that to go. I'm injecting at a constant flow rate. And maybe the pressure difference is going to be strong enough that I'll displace some of this oil that was trapped by capillarity. So that's the basic concept. But the idea is that what should be the size of the drops for this to work? If the drops are too small, they will flow without any problem. If they're too large, you're basically going to filter the drop out, and it won't go inside the porous media. So you need to design the size distribution of your emulsion with respect to the pore throat distribution of the reservoir that you want to work with, okay? So that's how we got into microfluidics looking at this problem. Again, the same microfluidic porous model is a regular network of throats with different sizes. Again, we use these sizes of 45, 75, and 100 micrometer, which are randomly distributed throughout the pore space. The same fluids, we have a mineral oil in an aqueous phase. We have to put surfactant in the water such that the emulsion is stable. So if I'm injecting an emulsion that's not stable, this won't work because the drops will coalesce. Now I start having very large drops inside the porous media, so that won't work, okay? And so we produce emulsions with two different size distribution. So what we call the small drop system, we basically sheared it for a longer time, and then we get this drop size distribution, and then we get what we call the large drop system that we don't shear, we change the, I'm sorry, we didn't change the time, change the rotation of the two racks. We get like a more spread drop distribution where I have drops that are larger than the small drop system. These emulsions were stable. As I mentioned, we put surfactant in the water. So even after a month, you see that the drop size distribution did not change. So the system was stable. The experimental setup is the following. We inject the porous micromodel was filled with water. We inject just the water to reach the permeability of that porous media. And then we inject a slug of emulsion, so a 7 pore volumes of emulsion, and then we follow that emulsion injection by the water injection. So I'm injecting a slug of water filled with drops, and then pure water again, okay? And then after steady state, we are measuring here the pressure, the pressure drop and the image, okay? So this is the setup with syringe pumps. The micromodel sits there in the inverted microscope such that we can see what's going on. So here's just a photo of the experimental setup. You cannot see the pumps. The pump is somewhere here, but you have the pressure transducer, and here's the micromodel sitting in the microscope. So an important point here. Remember, our pore throats were of around 45, 75, and 100 micrometers. If I have the small drop system, so 78% of the drop will flow through all the pore throats without any problem, because the smallest pore throat is around 40 micrometers. Okay? And if I have the large drop system, only 54% of the drops would flow without any problem. So I'm changing the number of candidate drops that would get trapped in pore throats, okay? It's not so simple because once a large drop blocks a pore throat, it may block the coming of a smaller drop because that pore throat is already blocked, okay? So you get like a traffic jam of drops in a pore throat that was initially blocked by a large drop. Okay, so here's an experiment, just a visualization of like a macroscopic visualization of the large drop system at low capillary number. See, since I have a large drop system, you can see that I'm already creating this traffic jam here. There's a lot of drops that get trapped. You see the small drops can flow through. Some of them get trapped again. And when we can measure the pressure evolution with time. So this yellow region is where I'm injecting emulsion, okay? So I had like a constant pressure drop with the water. I inject emulsion, the pressure goes up. It reaches an oscillatory state. And then when I inject water back, I remove some of the drops that were trapped, but not all of them. You can see that I'm just injecting water here, but the pressure drop is higher than what we get before. So this is the change of mobility of the water phase that we are interested in, okay? Again, if I want to displace oil, I want to make it hard for the water to flow and easy for the oil to flow. If I run exactly the same system, but at a higher flow rate, so a higher capillary number, you see that there's very little drop retention. Because remember what is the mechanism? The mechanism is that I have a drop that gets plugged in a pore throat, okay? So if the pressure difference is high enough, it will overcome the capillary pressure and that drop will flow through, okay? So this gives a very important mechanism, is that I can trap or untrap a drop by controlling the flow rate. This is important because when you're injecting stuff on a reservoir, people get nervous of blocking the injection well, okay? So you don't want to, what they call in the industry, like lose the injectivity of the well. So if I'm injecting this emulsion, the capillary number, the pressure gradient near the injection well is high enough that these drops will flow without any problem. As you flow away from the injection well, the pressure drop goes down. It comes to a point that now the pressure difference is not strong enough to push the drops through the pore throats. And that's where you're going to start blocking your drops. So in principle, that's like our holy grail. We can design different systems to block in different areas of the reservoir, controlling this blocking by the pressure gradient, okay? We are not there, but that's where we want to get. So an important result here for interest of time that I'm going to show is that I'm going to compare or characterize the emulsion blocking by making a ratio of the pressure difference that I get at the end of the emulsion injection to the pressure difference that I had with pure water system in the beginning, okay? So this is what we're going to call the resistivity factor. This is how much the emulsion is diminishing the ability of the water to flow, okay? Oh, here's just a visualization of this process that I mentioned. You see there's a large drop that's blocking this pore. The pressure is going up, and then the pressure was strong enough that it was able to squeeze that drop through that pore throat. Okay, and that's why when you see the pressure difference, I didn't call your attention to that, but the pressure difference was oscillating. The oscillatory nature of the pressure difference is associated with this blocking and unblocking dynamics that you get inside the porous medium. Okay, again, I'm going to show this what we call this RF, which is the ratio between the pressure drop of the emulsion flow to the pressure drop of the pure water. So the higher is this RF, it means the more you're blocking the water path. So better it's going to be for having an oil displacement. Okay, so this is the RF as a function of capillary number and as a function also of the drop size distribution. One important point here is that if the capillary number is high enough, as I showed you in the video, very few drops get trapped because the pressure difference is high enough that you can flow through. You win the capillary pressure so the drops can flow through. So there's very little effect of the presence of the drops, and the size doesn't really matter much. You get the same RF with large and small drops. If you go below a critical capillary number, you start seeing the reduction of the mobility of the water phase associated with the presence of these drops, okay? And as expected, the smallest the capillary number, so the weakest is your pressure difference, so fewer drop you're able to displace. Okay? And then you get a higher reduction of the mobility if you have larger drops, because you're blocking more pores, okay? So in principle, we can design an emulsion that will have the right critical capillary number. So I want to be able to move this to the left or to the right by designing the emulsion, okay? And also how much I'm changing the mobility of the water phase by controlling the size distribution. We only look at 2 size distribution here, so the problem gets more complex. And our porous media was very simple with only 3 pore throat distribution. So what we need to move in is to have like a more broadly distributed pore size distribution, and then examine different drop size distribution and see how do we get these mobility changes. That's future work. So why we want to change the mobility of the water phase? To displace oil, okay? At the end, that's the goal of the oil-producing company. So we did a simple experiment here where we had our porous media micromodel saturated with oil, so everything was yellow. We inject water. So water flows through forming a viscous finger, because since water is less viscous than the water, this displacement is unstable. Okay, so water will create an easy way out, and you leave all this oil behind. So you have 2 reasons for the oil to be behind. One is that the water never got there. So this whole area here of our porous media was never touched by water because of this macroscopic instability of the displacement flow. And you have oil that's trapped as a residual oil saturation. So water got there, but it was not able to displace these oil ganglia. So what we did now, so just for reference, the remaining oil saturation was close to 60%. So we only were able to recover 40% of the oil that was inside the porous media, okay? Now we inject a slug of emulsion. So I'm injecting water with small drops. The drops will get blocked somewhere, and after a while, we inject water back again. And then you can see probably all this yellow that you're seeing here is probably drops that I'm injecting with the water, okay? And then when we inject water back again, some of that pore was blocked, and the water found other ways to go. And as it found other ways to go, it displaces oil. So at the end, we went from a remaining oil saturation of 60% to a remaining oil saturation of 45%. So there was a huge gain in terms of volume of oil that was displaced by this alternate emulsion water injection. Again, I think microfluidics here gives the clear picture of what's going on inside of where the physics matter, where is the pore scale. So once we understand what's the physics in the pore scale, we can try to go and get better optimization of the process, even if the results in a macroscopic scale, as, for example, getting more oil out of your porous media. So we can say that emulsion reduces the water phase mobility. The emulsion drop size need to be close to the pore throat diameter. As I mentioned, I don't want all the drops to flow through, neither all the drops to get blocked. So I need to get an optimization of this drop size distribution. At high capillary number, the pressure drop is strong enough that the drops will just flow. So there's a critical capillary number where you see this transition from blocking and non-blocking. There's still lots to do. In terms of real application, we are working on these now in a couple of projects. You need stable emulsion for formulations, and this is going to be reservoir dependent. Because if you're producing oil, typically oil has a lot of surfactant, natural surfactant, and it's easy to form a water in oil emulsion because the surfactant is in the oil phase. If you're getting the produced water to produce oil in water emulsion, it's not simple because the oil doesn't like to be the dispersed phase. And the idea is not to bring new oil to the field. You want to use produced oil, treat that produced oil, and re-inject that water with oil in your reservoir to get more oil out, okay? And so we need to work in the chemistry of these formulation, stabilization of the reservoir, and it's really dependent on the oil composition. We need to study the blocking mechanism in fractured porous media, is the work that I showed you before. So everything we showed in terms of fracture there was no emulsion, it was just water and oil. But now what happens if I have drops? Because if the drops were designed with respect to the porous matrix pore throat, it will flow through the fracture without any problem. And you saw that the fracture is making our life worse. So maybe I want to block the fracture, not the porous matrix. So how can we go around solving this problem? And one point that we are working on is that if you're using an emulsion the only variable that you can control for the block capability is the size distribution. The interfacial tension is more or less constant, and it's going to be whatever you get from your stabilization process. So if I want to make an emotion block more strongly or not, if I could change the property of the interface, that will give another knob of control, because then I could have an interface that's very soft or an interface that's more rigid. So that's why we got into, instead of injecting an emotion, is another use of a capsule, but not to deliver anything. It's just forming drops that has a film of a polymer around it, such that if we control the polymer, we can make it very soft or very rigid. And then that will give another knob of control of the emotion that you're going to inject. If I want to block a lot, I'll make a rigid drop. If I don't want to block very strongly, I can make a softer drop. Okay, so we are doing, Rafael did his master's thesis on this. So these are the capsules that we are injecting. They are dyed here with this reddish color. You can see that the capsule flew through this three-dimensional porous media. And the remaining oil saturation without the injection of capsule was around 33. After the injection of capsule was around 26. This was not a good design. You see, most of the capsules got trapped here in the beginning. This capsule was too stiff for this situation here. So maybe we had to have a smaller or less rigid capsule to make it flow inside the porous media. That's why the reduction was not that huge as with the drops that I showed you before. So what's next? What are the next things that we are working on with microfluidics? So if we want to get more and more into this microfluidics used in reservoir engineering, one big limitation of all these applications that I showed you is that you're not running at reservoir conditions. So you're not running at high temperature, high pressure. So if you're using, if you want to study real system with oil, temperature and pressure is very important, because you can get change the composition of your oil. The light phases can become gas, so you have a more complex thermodynamics of this system. So we just purchased this setup here, which is able to do microfluidics at high pressure and high temperature. So this can reach 15,000 psi, which is around 80 megapascal, and then can go up to temperatures of 200 centigrades. And then their microfluidics chips are designed to be able to resist this high temperature and high pressure. So here's an example of a result that we already got in our lab. So you can study, even do like thermodynamic analysis of a fluid. So this is an oil that we kept inside a micro model. So you have these oil drops which are surrounded by a water phase, and then you can change the pressure of the system. And you can slowly change the pressure of the system until you start seeing some bubbles forming. So you're just measuring the bubble point of this system. So you can get like PVT data in hours, not in days or weeks that would take in a PVT cell. So you can run not only fluid characterization, but you can now run studies of injecting water, injecting emulsion, displacing oil, but displacing real oil, using the formulation that are in the field. So I think that's an important step to get the use of microfluidics in application to reservoir engineering. Okay, with that, I end my talk. I want to first thank the people that actually do the work. This is a picture, this is an old picture, we have our monthly birthday cakes. So this is probably from more than a year ago. Bruna was still pregnant, so her baby is around a year and a half already now. And I need to renew this picture. So it's a great team. It's a very diverse team. We have had like mechanical, chemical engineering, food science engineering, bioengineering. We have physicists, mathematicians, pharmacists working in our lab. So it's a very multidisciplinary team. I believe that that's very important. I think that a lot of things we do are multidisciplinary. We need this multidisciplinary in our group. I need to thank those who signed the check. For what I presented here was funded by CNPq, CAPES, and FAPERJ. And then some of the oil things were funded by Shell, Petrobras, and Repsol Sinopec. If you want to get more information, it's always outdated, but you can go to our homepage. And if you have any question about the research or about opportunities in the lab, you can just send me an email. And I want to end inviting you, if you have ever a chance to visit PUC and visit our lab and visit Rio, you're more than welcome. Thank you very much.
Thank you, Marcio. Thank you very much. I always learn a lot here in your talks, so I really appreciate that. And I have a lot of curiosities, but I have to give the opportunity to the audience.
All right.
Okay.
Sorry, I got the mic
yes.
first. So thanks for the talk. It's really interesting. I have a question going back to the problems of two-phase flow in fracture and valvular media. Did you try any numerical modeling of your microfluidic systems, and whether you have to take into account capillarity in such a case, or if you believe you can neglect it?
So we cannot neglect it in the porous matrix, but I believe that in the fracture, capillarity is probably not important because the pore size is big. And we are doing modeling. I didn't show here. We are using what's called, I don't know if you're familiar, Brinkman equation, which is, so we are using Brinkman equation to solve the flow through this valvular system and through the fractures. So basically we are solving Stokes flow in the fracture and VUGs, and then Darcy flow. And then the capillarity goes in the Darcy flow through the capillary pressure curve and the relative permeability curve of the porous matrix. So in a sense, it's input in the model. We are not doing like pore scale modeling of the coupled system. And then that's what I talked with Pablo the other day. It would be great to do some modeling with the techniques that he showed here yesterday. Yes.
All right. Thanks.
Mm-hmm.
Okay. This one.
Hi, Marcio. Thank you for the talk. I was wondering about this last part that you said about the control of the other knob of control of the droplet size and etc. If you put like a polymer on the surface of the drops, that could increase, for instance, the rate of coalescence, and could end up in a variable drop size inside the reservoir?
No, so the idea is to have a polymer that's like a polymer shell. So you have like a solid surface, so they won't coalesce. So it's like a capsule. So it's not, so we form a capsule with a solid surface, and then we have made tests so they're stable. So you can press them against each other. It's just like a solid surface.
Ah, okay. So the effect is the contrary. So you want to prevent coalescence.
And more importantly, in this case, we want to control how hard or easy it is to deform the drop to go through the pore throat. So if I have like a stiff shell, I will need a much higher pressure difference to squeeze that drop through a pore throat. If I have a less stiff shell, like a drop, it's going to be easier for it to flow through.
Okay, thank you.
Mm-hmm. Okay, thank you. Your turn.
Okay, thanks. A very, very nice talk, Professor Marcio. But I have a question is, have you considered the presence of microparticles in any of the experiments, or they're not relevant at all in the investigation?
You mean particles that we put there on
grains?
purpose?
Yeah, from...
Oh, grains from a real car? No.
Yeah.
So yeah, we don't consider, and it happens like depending on, mainly with carbonates. If you have a carbonate, depending on the water composition that you're injecting, you may get some fines or grains that are carried, and those grains may block the pore. Yeah, we haven't looked at this problem. So what people typically do in practice is to control the formulation of the water such that it doesn't react with the rock matrix to get these grains. Because once the grains are free to go, they can go and block your pore throats down the plug, yes. Yeah, but we haven't considered that.
Okay, I was told that just only 3 questions, so that's 3.5, quickly.
So, thank you, Marcio. I agree with Claudio that it's always a pleasure to learn from your talks. Just a curiosity, you talk at the end about the real conditions in the field. How they pump these fluids, so they work at constant pressure, constant flow rate, or you have these curves like the centrifugal ones?
Yeah, you typically have like a centrifugal pump that you have a curve, and there is like limitations in pressure Because if the pressure goes too high, you may fracture your reservoir. You don't want to do that, not in an uncontrolled way. So it's typically like a centrifugal type pump, and then you have regulators that don't allow the pressure to go beyond a certain values. Yes. So it's a mix.
Yeah. Okay, just to have whole numbers, I will complete the fourth one. Okay. So I know that reservoirs have very meters in depth. So have you ever considered the effect of gravity? Because you have solutions, I mean, oil and water with different densities. And I think that even at the level of the chip should be some effect. Because your experiments are always with the chip in that situation. Have you ever tried like this or like this?
No.
No?
Yeah.
Okay.
But that's a good point. Like if you go to a reservoir scale, you inject water will, depending on and some reservoirs are not very, although they're deep, they're not very, I don't know how, the height of the reservoir is not very high. Okay. So there are reservoirs that are only like 50 or 100 meters, which is not huge.
Yes, but I saw some pressure values around 10 kilopascal, so that's the order of some effect.
Yeah. Okay. So it may be important.
Okay, if you did those experiments, you send me a picture, but I would like to see that.
Okay.
Okay, thank you, Marcio. Thank you very much.